When you think about landing on the moon, what comes to mind? Probably those iconic Apollo images, right? Flat, sunny, pretty safe-looking plains. Well, for the big return with Artemis III, NASA is basically tearing up that old playbook. They're aiming for a spot that's pretty much the exact opposite. The most dangerous, most treacherous, you might even say forbidden region on the entire moon.
Okay, so let's break this down, because the difference here is just staggering. Look at the Apollo sites. NASA picked those spots for one reason: safety. They were near the equator, nice and flat, and had plenty of sunlight. Now, the Artemis target at the South Pole, it's the polar opposite. We're talking jagged, totally unpredictable terrain, a world of blinding light right next to pitch black shadows that have never, ever seen the sun.
So, you gotta be asking the same question I was. Why, right? Why would NASA ditch the tried and true, safe spots for what is, without a doubt, a monumental challenge for any engineer or pilot? I mean, this is our first trip back to the surface in over half a century. Why take such a huge risk?
Well, the answer is actually pretty straightforward, and it's a game changer. This mission isn't just about repeating the past, planting a flag and grabbing some rocks. No, this is about building a future in space. And to do that, they need to get their hands on a resource that's so unbelievably critical, it makes gold look like, well, just a boring old rock.
And a key to this whole thing is something called a permanently shadowed region, or a PSR for short. So picture these incredibly deep craters at the moon's poles. The sun is always super low on the horizon there, so its light just skims right over the top. The floors of these craters, they never ever see the sun. We're talking not a single photon of direct sunlight has hit these spots for billions of years. It's just mind-boggling. And it's really hard to wrap your head around just how extreme these places are. I mean, the temperatures just plummet, hundreds and hundreds of degrees below zero. These PSRs are basically cosmic deep freezes. In fact, they are officially the coldest places we have ever measured in our entire solar system. Get this, they're even colder than the surface of Pluto.
So what's been hiding in this cosmic freezer for eons? The holy grail of space exploration: water. And not just a little bit, we're talking massive deposits of water ice, which NASA probes have already confirmed. And that is the prize. Because out there in the vacuum of space, water is everything. It's not just for drinking, it's the oxygen you need to breathe, and most importantly, it's rocket fuel.
But here's the catch, and it's a big one. The very thing that protects all that precious ice, that permanent, deep shadow, is the exact same thing that makes trying to land anywhere near it a complete and total engineering nightmare. Seriously, this isn't just a tough problem to solve, it's a whole new category of difficult. And this really shows you why. Think about it. Near the equator, where Apollo landed, the sun is high in the sky. You get short, clear, predictable shadows. No big deal. But at the pole, the sun is always hugging the horizon. And that creates these bizarre, miles-long shadows that stretch out like daggers across the terrain. And hidden inside those shadows are all sorts of dangers: giant boulders, steep crater rims that would be completely invisible to a normal camera. So here's the really scary part. This is how it can trick the tech. The lander's computer scans the ground looking for a flat spot, right? And it sees this long, dark patch that looks perfectly smooth: the shadow. So the computer says, great, safe landing zone here. The lander fires its thrusters, adjusts its course, and flies straight into a hidden crater wall or a house-sized boulder. Mission over. Catastrophic failure. So to get around this, the Artemis landers need to be, well, smarter than any lander we've ever built. They're going to be packed with the most advanced autonomous landing tech you can imagine. We're talking stuff like LiDAR. That's a system that shoots out lasers to create a super detailed 3D map of the ground in real time. It allows the computer to actually see the shape of the terrain inside the shadow to tell the difference between a flat spot and a deadly trop. And even with all that, you can bet the astronauts will have their hands on the controls, ready to take over in a split second. So how is NASA planning to pull this off? Well, it's not just about brute forcing a landing. Their whole strategy is actually way more clever. It's built around exploiting this absolutely brilliant paradox, this weird little quirk of physics that only happens right there at the lunar South Pole. And here it is. It's so cool. While the floors of the craters are trapped in eternal darkness, the rims of those very same craters, these high-up ridges, are bathed in almost constant sunlight. They literally call them peaks of eternal light. So you have the prize, all that water ice, sitting right next to the power source, a virtually endless supply of solar energy. It's the perfect setup. And this paradox is what makes the whole Artemis base camp idea possible. It's a beautiful strategy. Step 1. Land on one of those safe, sunlit ridges that overlooks the dark craters. Step 2. Set up your solar panels on the peaks of eternal light to get uninterrupted 24/7 power. And then, from that base, you can safely send your rovers or even your astronauts down into the shadows to get the ice. This is the only place on the entire moon where a long-term, sustainable human base is even feasible. And that word, sustainable, that changes everything. It means the South Pole stops being just a cool place to do science. It becomes infrastructure. It becomes a strategic outpost that unlocks the rest of the solar system. You heard me right. It's literally going to be the gas station of the solar system, fueling up future missions to Mars and beyond. So how does that even work? How do you turn ice into rocket fuel? It's actually some beautifully simple chemistry. First, you mine the ice. Then you use all that solar power to melt it. After that, you run an electric current through the water, a process called electrolysis. That electricity splits the water molecules, H2O, right back into their components, hydrogen and oxygen. You collect those, liquefy them, and boom. You've got liquid oxygen and liquid hydrogen, which just happen to be the most powerful and efficient rocket propellant known to science. You see, the biggest problem in space travel, the thing that holds everything back, is something engineers call the tyranny of the rocket equation. Basically, it means you have to use a ton of fuel just to lift the fuel you'll need later. It's a vicious cycle. Most of the energy from a launch from Earth is spent just fighting our planet's gravity. But what if you could launch a spaceship with mostly empty tanks, get to the moon, where gravity is much weaker, and then fill it up for the long haul to Mars? You've just completely rewritten the rules of space travel. The moon isn't the final stop anymore. It's the critical stepping stone to everywhere else. And that is why the stakes for Artemis III are so incredibly high. This isn't just another mission. It's a fundamental shift in how we approach space. We're moving past the age of just visiting other worlds. This is about finally figuring out how to live there. So yeah, the gamble here is absolutely immense, but the potential payoff, it could literally redefine humanity's future in space. This mission turns the moon from a monument to past glory into a launch pad for our future. And that makes the lunar South Pole, without a doubt, the most strategic piece of real estate in the entire solar system, which leaves us with one very big question. Who's going to get to control it?